some time that you can talk about a data set or talk about a procedure, do some introduction, summary, a little bit. So, we have up to that amount of time. Some will go
I feel like
fast.
mine's not going to take that much time.
Well, it's they might not take the full time, but we're kind of allocating that. Right? If we have 5, it's about 10 minutes. To kind of set up, get their introductions and questions.
Then the final write-up is due Friday.
Yes,
Okay.
principally to do that. I mean, it'd be good to get it done, then I can grade it and do some feedback. Right. But if anybody says that absolutely need, it has to get done. I'm setting the due date there, but it might be better to write something better. I want people to try to get it done there, but you want to have the presentation done. If that carried over, it wouldn't be the end of the world. It cuts into your time to do everything else. I've heard some people have multiple presentations, multiple papers, so it's kind of a management. And the final is Tuesday. So absolutely, I have to have a Tuesday to grade it and put the grades in. The Friday would be best, and that's when the due date is. But if there's special circumstances with everything piling up for somebody, then, we live in an electronic world, so it could be come in, a little bit editing, make it a little bit better, but it cuts into your time. So we have a sign-up sheet for presentations. We've got a couple sign up for Wednesday, but if anybody else can sign up and do something on Wednesday,
That's fine.
we'll do that.
Are you taking that too?
What?
The mouse summoner?
That's since Caleb took that last year, we had our meet and greet. She got out of that, so I sorry about it.
She said it was like,
Yeah.
Welcome back. Break. There's a pad of paper that's going around that has some sign up for presentations. A couple had signed up for Wednesday. It's filling up on Friday. There's nothing in this classroom after our class, so we do have this classroom on Friday until 3:05. So that would facilitate more presentations on Friday, but it's good to get some done on Wednesday, so that day's not too long, and we don't have to just rush through all those. We'll be a little more comfortable if more can go Wednesday. When you do the presentations on Wednesday, you don't have to turn in the final write-up at that time. You can modify things and finish that up and turn it in later. Right. So the presentations with this schedule of 5 or some amount on Wednesday and the others on Friday, about 10 to 12 minutes is available, right? Some will do a little bit. I think that might be just about all. And this is somebody's 451. Is your paper from?
Is it from today?
Yes, it's from the 20th, so I don't know.
Maybe it's
I'm under yours, you're in that case, right? Got to wait around with it. But so we have a couple for Wednesday, and then it looks like 8, and there's one's a double, so that's 9. So there's somebody, I'll try to figure out if anybody is left out. So the first thing to mention, right, is so you probably got an email about course evaluations. If you log into the web Canvas, it'll prompt you to do this. I encourage you to evaluate those. Those are anonymous. I don't see who does each evaluation. I don't see them at all until I turn in my grades. So they can't impact the grades that I give. I look at them always. Look at the scores, think about the ratings, look at the comments. You know, some students have incorporated, I wish we did this, or I wish we did that, or I like this, I like this, I want to do that more. And so I usually follow those things. It's likely that maybe I'll teach this course again next year or in some future iteration. And so different things can be, you know, recommended. Do you want more computing, less computing, more theory, less theory? You know, I look at those and I think that they do help with improving the courses over time. This is the second time I've taught this course here, and so, you know, each time I teach it, I probably change out about a third of the examples or modify presentations on parts of it, and so it's always changing and hopefully getting better and more relevant. So I encourage you to do those. Response rate, getting that higher is always good. It gives me more information and more feedback, right? For that, let's just say a little bit about the presentations. So those are Wednesday and Friday. So it's scheduled so you could have 10 minutes or even 12 minutes. Many conferences will give you 10 minutes or 12 minutes to do a presentation. And presenting work that you've been doing for a while, it always seems kind of like a rush to get things in there. So the best presentations don't necessarily pack it full, but they take time to explain what's there. Right? If there's a graph, you know, what's on the x-axis, what's on the y-axis, what do points mean, what patterns do you see, so you can say a lot about that. You can add a little content to things. You're going to do a t-test or do something, you know, do a different procedure or talk about an example. You know, you can talk about what did it mean in context of this class. We'll be doing mathematical statistics, properties of different procedures. So a little short summary of what that is could add just a little bit of content to the presentation, connect it to the class. If you have a more substantial example you're working on, maybe most of your time would be done on that. You can show us graphs of the data. You can show us summary statistics. Once you do a procedure, get some inference statements, a confidence interval. You can interpret it in the context, say what it means to your example. You know, if you have a smaller, you know, data set or example, you can speculate on what else you would like to know. You know, what would have else been important for the design? What could be limitations of that? You know, some of our procedures had, you know, you could check normality with some graphs, if that's, you know, do a sampling distribution, if you know, bootstrap. What does the sampling distribution look like? Is it kind of normal? So there's ways that you can kind of dig into things, and all that will add up to the time. And if you present kind of an introduction with a hypothesis, and then some results and work, and some interpretation, and kind of a conclusion, it can fill up 10 minutes pretty fast, right? If you go a little bit shorter, that's not a problem. If you are prepared things and think you have 4 slides and it's going to take you 2 minutes to present, maybe there's a little bit more you can think about, right? Or you could share it with me, and maybe I can get some suggestions for adding things to it to make it a little more substantial presentation. Right? So, you know, you can think about you're presenting to people who have had a similar course, similar backgrounds. You don't necessarily need to find every little detail, but just talk about the concept we've introduced in the context of the problem. But, you know, give enough background on the material that's there so others can try to understand what's going on. If you see anything interesting, like outliers or unusual patterns, or if it's a result that's, you know, surprising in any way, be sure to explain that, why you think it's interesting, and so on. You can prepare them with PowerPoint or Word documents or different styles of things, or LaTeX has a different presentation formats if you use that software, Scientific Word. But, you know, maybe for many, you know, the PowerPoint would be, or other open software. If you send it to me, you know, at least by the day before the presentation, I'll get them kind of ordered so it's kind of efficient going through that. You know, I'll take notes on each one and then share some of those notes back with you about that. Right. So, but any questions about the presentations and kind of things you want to emphasize? If you have ideas about things that you might have done or things that you might, you know, and we haven't exactly covered those, but you think this would be relevant to think about, you might do the experiment a different way. You could, you know, trying to speculate or suggest those things. That's kind of interesting. You have to do those mental exercises to try to think about how could you do things better. So that's always interesting to kind of think about. Okay, so that's the presentations. That's there, and the evaluations. So a little bit about a little summary, right? So there's a couple homework solutions that I'll post, right? So so kind of this is more related to this final, since I'm on this page of my notes. Solutions will be posted. Solutions will be posted. I'll also post some different study problems, right, with some solutions, right, so that it'll be something else to look at, particularly for the more recent material. Looking at, you know, exam 1 and 2, there's some solutions that are posted for that, the homework and the solutions. So a number of those things would be relevant for that. Right. I guess the other thing, just to make sure that things are clear, the kind of the paper, the write-up. So it says on there, you know, that it's due this Friday. You know, so I am sympathetic that people have many different homeworks, presentations, projects, and things going on. So it's set like that so that you do get it done, that the majority does get it done, then I can grade it and give it back to you when we have our final, so you get some feedback on this thing that they're working on. But if you have multiple ones, it's kind of pressed to do all this and do a good job. Now, that if you don't turn it in on Friday, but need to send it to me electronically or submit it on Monday, or, you know, the absolute end is the Tuesday at the exam, so that I can grade it and submit grades. It doesn't make sense to go beyond that, I think. Right? For you, the consequences, if you drag it on and don't get it done, you know, then it cuts into your studying for other things. But maybe you have 3 classes where you have papers, and we also have a final right on that Tuesday, so you need to study for that. So there's a consequence to you if you don't get it done there. But since it's an individual project and write up, you know, let me know if you anticipate that it would come in later, but by and large, I think most of you, as you're writing up, making the presentation all together, it would make a lot of sense to hand it on Friday. So the due date is put on Friday, and the other ones can be kind of exceptions if you have particularly hard cases. Right? Okay, so I'm sympathetic to that, the piling on that happens sometimes. Right, so in terms of kind of summary of the course, this course has been about mathematical statistics and how somebody who's developing statistical procedures thinks about different things that could be done with data to reach a conclusion. Right, so you want to take off the data and do a conclusion about something. So, you know, I often draw this idea that there's some population out there that you'd like to study. And describing that population are its characteristics, which are often encoded in parameters. Generally, we call that theta for some generic parameter, but in specific cases, it might be the mean or the standard deviation or a proportion. In linear regression, the expected value of a random variable is related to a linear equation. So there's these coefficients that are parameters, and it gets more complex from there, right? Instead of a proportion, you could have a p over 1 minus p, or an odds, or the log of that, a log odds. So you can have different types of parameters. And you want to know those things. If we knew them, we'd be done, right? That would be kind of the truth or the state of nature or the answer we want. So you're going to collect data, you take a sample of data somehow, x1, x2, right, up to xn. For some problems, there's a y and an x, so there's multiple variables. Sometimes the sampling is random sample. Sometimes it's more convenience or observational studies. Sometimes it's a design experiment. So there's all different ways that goes in. We can do various sample summaries, and more generally, things we call statistics. Right? So summaries of those. For these different things, you might consider x bar, or the standard deviation, or the sample proportion, or in the linear regression context, we estimate parameters, and we'll just put little hats on those, meaning that these are things we compute from the data to kind of get optimal values and things like that, right? So we get these estimates, and then we want to do inference, right? We want to do inference to use our data to say where these things are, right? And so we've investigated different ways of doing that and different rationales, right? And the two main rationales are more of a frequency approach. We want things that have good frequency properties in terms of confidence intervals or low error rates and things like that, right? Or Bayes, looking at a probability statement. So that was kind of the other way. And sometimes that inference got expressed as confidence, as intervals, sometimes as hypothesis test results, but it's still saying things about the parameters based on the data with hopefully low error rates, right? And so part of the course is understanding, thinking about these inference things as procedures, right? So the inference procedures are things that you set up a protocol. What are you going to do when you get the data? How are you going to use it? And once you get the data, you follow through with that, and you study the procedures so that you think that they're going to work well in many cases, right? And so the kind of the frequency-based procedures, frequentist, we looked at things like Bootstrap to get standard errors. We looked at maximum likelihood estimation and what happens in large samples and large sample results. This is kind of like a central limit theorem thing. And then we express things, confidence intervals, hypothesis tests. The confidence interval is tied to sampling distributions. What would happen to our statistics if we had repeated it many, many, many times, right? And so we came up with a rationale that you would think this is the sampling distribution. We would kind of invert it to make a statement and come up with an interval, right? And those intervals, we didn't, the confidence interval either covers the parameter or not, but it had the property that it had 95% coverage. So in the long run, 95% of the time, we think our intervals, about 95% of them would cover and 5% would miss. And if that's true, then it comes with an interval, an estimate, an interval, and a certain guarantee or a certain quality level. Right? Is it going to make it 50% of the time? Well, that's not very good. 95% of the time is pretty good. 99% would be better. And depending on the data distribution and the sample size and exactly what we're doing, it could have a different width. And the hypothesis testing kind of had its own lingo, right? You specify some null and alternative hypotheses. You think about type 1 and type 2 errors. You have an alpha, which is our significance level. And you have a statistic that you compute. You have a reference distribution. You compare it to some distribution. And you could possibly compute some p-value. And again, this is kind of under the frequency approach. If the null hypothesis is true, what's the chance that you were as extreme or more extreme than what you actually saw if the null hypothesis is true? So kind of some measurement of kind of surprise that's there. So a lot of lingo, but it's kind of doing the same thing. We still want to say something about where that parameter is in the population, and we focus on some specific questions rather than just say where it is. There's some dichotomy, some duality between these things. But again, whereas we want the confidence intervals to cover well, we want these hypotheses to not make too many errors. So if the null hypothesis is true, we don't want to reject it very often. We don't want to make a false positive. And then we thought about power or sample size in relationship to the type 2 errors. Right? Even if you're not going to make the type 1 errors very often, you can guarantee this by defining your procedure, but you can think about needing good sample size to be able to detect something that's actually different. Right? Same thing up here, like a confidence interval. You want it to be narrow, right? So you got to think about sample size to do that. So these things have properties. The other big contrast, so within the hypothesis test, to evaluate some of these things, we really use some idea of randomization or permutation. Those were really kind of ideas for implementing some of this frequency ideas. Right? So if the null hypothesis is true and you have two groups, well, under very strict null hypothesis, there's no difference at all. It's just random. Who's in group 1, who's in group 2. Right? You can randomly create them, and we can use that simulation. So among the possible alternatives, possible different realities that might be there, how unusual is the one we saw? Right? Is the observed difference really big relative to what was possible through just randomization? The other big thing is phase. Kind of a Bayesian approach. And here we specify some prior distribution for our data, and then you have a model that says something about the data given a parameter. How does the parameter affect the data through a probability structure? And then we come up with a posterior distribution. F of beta given x. And so it's through that then that you can summarize things. And you don't need to think about other data. You just have probabilities. Like what's the central part of the probability distribution? What would be the average of random values from that probability distribution? What's the mean, the average value, expected value under that distribution? So it becomes a different approach. It's still trying to say what the probability that is, that what the parameter is. It just has this other rationale. If it can be very useful if you do have prior information, prior studies that give you some guidance. And so in some more complex problems, there's some advantages as I see. But anyway, it's a different philosophical kind of approach. But also a different procedure, right? You take the simple 95% interval of this, you have an interval. Right? You could ask the question, is your Bayesian procedure well calibrated? If you say it's a 95% posterior, what percent of those intervals cover? And if there is some truth out there, say there's really some value, like the speed of light or the weight of something, right? And if you could have the entire population and you would know that value, well, there you go. That would be it. But do most of the intervals that you make, do they cover? And generally they do, as the model is right and the sample size gets large. Or even if your prior opinion's a little wonky, it still tends to converge. Just like the other procedures, they tend to focus in through limits. So that's kind of the world that we've looked at, emphasizing these things as procedures that have properties that we can evaluate. We can figure out some mathematical theory to show whether they're good or not. In other cases, maybe we have simulation evidence to suggest how they work. Right? Once you deviate from some assumptions, like your small sample size, skewed data, it's sometimes easier to simulate many, 1,000 times, 10,000 times, and see, does the procedure give you a good answer? Right? When you're kind of doing one of these things. So should we use the mean, the trim mean, the median? Should we use different things? Which ones have lower alpha values? Which ones have greater power? We can compare all these procedures and come up with optimal. And so in the world of mathematical statistics, as the models get more advanced, it becomes harder to estimate things, harder to set up criteria to balance different objectives, but still a lot of the same questions get asked. Right? So that's what we've been doing. Hopefully that it's shown some insight behind what goes into some of the standard procedures. And then along the way, we've learned some standard procedures that if you go out and do applied statistics, you would see used a lot. So from 11/22, that Friday, just before break, we talked about material on the final. And so I'll just do a short list of that, but you could look back to the notes from that time to get a little more detail. I have the Bayes binomial inference for a proportion, saying something a little bit about that. So say you have a certain beta distribution, beta binomial, right? Beta distribution for a prior on a proportion, it's a binomial model. The posterior distribution ends up being a beta distribution. And we looked at what the mean is, something about how to figure out the alpha beta parameters, if it was the mean and variance, and then something about summary. Very likely I would give you a simulation, results, a histogram with simulated values, or some other summaries for you to state, right? But this ultimately gives you an interval, and you can just say that's where we think it is, right? So that, in chapter 10, there's the x squared statistic. We might figure out the expected value under some assumptions. We would compare to a chi-square distribution. So either I'd give you a table or a picture, something like that, to work with, to be able to say is it unusual or not. There is also a description of a permutation test. You have two groups, a certain number of successes in one group and a certain number of successes in the other group. And it's just completely, the null hypothesis is there's no difference in the rates. Then you could just randomly permute the counts and come up with different values of the statistic under all the permutations. And then so instead of using the chi-square, we can use the simulation based thing. We also did a Fisher exact test, but that's I'm going to focus on these parts of it. Right? Chapter 8 was about hypothesis testing. So on this one, I want to focus on a single sample for a mean. We did a t-test for this. So our t statistic was, from a hypothesis test versus a mu sub 0, with S over the square root of n, and we used degrees of freedom here of n minus 1. Right? And we could do a test. The contrast using the t distribution, right, was a bootstrap t. So I think that's an important concept, that the sampling distribution might not be exactly symmetric. If we had a bit more accurate description of that, we can use that for testing. So we've described a couple times, how do you set up a bootstrap, right? So you could expect, a question, describe implementing the bootstrap t. Right? Because if you can describe that well, it'll carry you through a number of different types of applications. You have this t statistic under our null, that we calculate. If we do some bootstraps, we can get a bunch of different t's that are consistent with the null hypothesis. And so if our observed statistic is unusual based on those simulations, then we reject the null hypothesis, instead of just going to a symmetric, nicely shaped t distribution. So that's what we'll do. There's some discussion of what is a type 1 or type 2 errors. just the concept of power. I won't make you do a numerical calculation to do that, but you might draw some graphs or describe what makes a test powerful, right? The bigger sample size. Why does that matter, right? It affects the sampling distribution. It's narrower about the alternative, so if one is true versus the other, it's a narrow sampling distribution. You can tell, is it this one or is it that one? Okay, so that's on there. Chapter 7 had a confidence interval procedures, and here it would either be one proportion or two proportions. So let's limit it to that. Right? We did things with means and some other things, but that's enough, right? So this one, we'd have a sample proportion plus or minus a z-value for 95%. And p hat, 1 minus p hat over n as a standard error. And in this one, you have p1 hat minus p2 hat. You have a difference of proportions, plus or minus. Use normal again. Again, that's 95% for those things. But now the standard error is the square root of the sum of the estimated variances. There was a more complicated one with the Wilson one, but this is fine for our computations. If you use the software, it would give you just a little adjusted thing, which makes more difference if you have a small sample size. So, you would have those. And it's good to interpret the interval in the context of a problem, right? And then also say, why does this interval make sense? Not necessarily going through all the mathematics or rearranging terms, but conceptually, why is an interval good? Right? It's not going to be 100% accurate. I mean, some of them will miss. Right? You get some funny samples 5% of the time, right? It's unavoidable. But 95% of these intervals cover the real thing, then that's pretty acceptable. Right? And if it does miss, probably doesn't miss by a lot. Probably misses on the margins a little bit. So it could still be useful. Right? I'll give you one to go back to something that we did. We had this maximum likelihood procedure, procedure, right, where we got the likelihood and took a derivative with respect to a parameter, and that ended up being our MLE value, and we kind of talked about what that was, right? So kind of going through that and talking about why did we maximize the likelihood. On the previous exams, that would be a good model for how I might ask about it, right? Try to step through so it's not kind of an entire question. You either know exactly what to do or not, but kind of in pieces. Here's the likelihood, multiply them together, show that this is the MLE, something like that, right? And kind of the other parts, I just talked about it before, but what is a sampling distribution? What do we mean by that concept? That was the chapter that we looked at that talked about that. Why do sampling distributions differ between different estimators? Why, how they affected? And so connected to that is properties of estimators, or the procedures. So there'll be, instead of doing the probability theory to derive a lot of expected values and variances, I don't mean that so much more the concept of, if I had two estimators and I could simulate them 10,000 times each, and I showed you graphs of their two sampling distributions, would one be a better estimator than others? Bias, variance, kind of come into play. So those type of things would be on the final and before last week. We talked a little bit more about that. It's kind of repeating, but I kind of look back at that, and this is a little bit more distilled. But any questions about? But not everything. It's kind of focused down on these things. So we can look at an example, right? So let's say you randomly pick 300 passengers on an airline, passengers on an airlines. So I don't mean just one airplane. I mean across the entire country. You have the thousands and thousands of people that are flying. I picked 300, right? So they're on different flights all over the place, right? And we ask if the recent flight was more stressful than expected. And then they answer yes or no. Right? Now let's say this is Pan Am, right? Right. Pan Am went bankrupt. Actually, I went on Wikipedia and did a search for defunct airlines, and there's hundreds of them. It's really all these little ones you never heard of that started up, had a few planes, and then went bankrupt. But Pan Am, of course, was the premier American airline to the world in the 50s, 60s, but then eventually went bankrupt. So, and let's say the data, 120 say yes, and then 180 say no. And there's 300 total. So I think, is it more stressful than you expected? People might have thought it was stressful anyway and just kind of expected it. So these are just made up data just to get some numbers. So what do we want to know? What parameter are we actually looking at? What is the parameter? What parameter can we estimate from that?
Proportion.
Yeah. Well, proportion.
Oh,
probably.
well, yeah. Proportion.
Proportion. So P, in symbols, some type of average rate, proportion. So P, maybe for Pan Am. Right. So this would be proportion, right, of all passengers saying yes. Yes to this question, that it was more stressful than expected. Doesn't mean if they say no, it doesn't mean that it's not stressful. It just means that they expected it. So what, we can do a confidence interval for this. 95% confidence interval for this Pan Am proportion. All right, so P hat plus or minus are 1.96. P hat 1 minus P hat over N. Right, so that's actually 0.4. This P hat plus or minus 1.96, 0.4. 1 minus that is 0.6. We had our 300 people. And so this gives a confidence interval of 0.346 up to 0.457. So how would you interpret that interval? What type of statement could you make that says what this tells me what that is?
95% confident the true proportion lies in between 35%.
So you're going to repeat the phrase, something like we're 95% confident that this interval covers the true proportion, or the true proportion lies in that interval, right? Right. Yep. So it looks like it's more than a third, but less than 1/2. Right. Say yes, it was more stressful than I thought. 1 minus that, you could take 1 minus these 2 endpoints and get the proportion would say no. Assuming everybody answered and you don't have any don't knows that are in there. Should this interval work well? Right, we might check, no, this is kind of based on, this is for 95%. 99% would have to be wider. 90% would be narrower, but 95% seems like a reasonable percent coverage. It is using normality to get that 1.96.
Our sample size might not be big enough.
Yeah, if our sample size is 300, right, you would think about sample if this was 30, might be smaller. It's just using a simple limit theorem for proportions. N times P hat greater than 10, N times 1 minus P hat greater than 10. We had 120 and 180, as the sample proportion, and 180 for the number of no's. So that's clearly big enough, the normal approximation should work well. So it should be pretty good as an interval. Now a Bayesian, right, it could be interested in that, but need to have a prior distribution, right? So a priori, we've been taking a beta distribution. Now, if this, I've kind of shown you the data, so it's kind of hard to think independently about the prior. Maybe I'd say the average is 1/2, and the standard deviation is, 0.25 or something, and you could solve for alpha and beta. Or maybe you just pick something. Right? So if I don't know much, and I think it's about 50-50, is it more stressful than not? It's not saying it's stressful, like I said. Well, you might have 3-3. Maybe that's somebody's prior distribution. Somebody else, say, no, I think it's more people are going to be more stressed in this recent thing with the storm coming and the holiday travel. You just don't estimate how bad it's going to be. So I'm going to do like this. Right? So the expectation here, right, is in general it's over alpha for alpha plus beta. So it'd be 3/6. So this person's saying it's 1/2. This person would be saying it's 30/40, adding those together. So 0.75, versus 0.50. This one's going to have a lot less variance as well. Right? This is pretty much more focused on those. Right? So maybe I'd show you a couple of pictures. Which picture corresponds to the prior distributions? Well, here it's not really hidden because it's there. This is a prior distribution on when the parameters are 3 and 3. Right? Centered at 1/2, symmetric, kind of spread out pretty far. I did a little experimenting here. Right? Right? This is when it's 30 and 10. Here's the other distribution. Right? So this person's centered around 0.75. Right? So knowing 3-3 and 30-10, if you figured out the means and the standard deviations, you could say which picture, which black line and red line, which priors do they go to? Given those choices. Right? So you can kind of describe those different distributions there. Right? Well, what's going to happen once we get our data? We get our data. X, we had 120. N minus X, the number of failures, is 180. So N as a whole is 300. What's the Bayesian summary? Right? So it's reasonable to say these are binomial. Right? 300 randomly selected people from a big population. No real reason to distinguish them. Are they flying on the West Coast, East Coast, Midwest? I don't have data on that. They're somewhere flying. Right? So they have the same proportion. Right? So X given P should be binomial. Right? Reasonable to use that model. So the posterior distribution we figured out is beta, alpha plus X and beta plus N minus X. Right? That's that posterior distribution. So what do these two people end up with? Right? You're going to add these numbers here to the priors and come up with a couple different priors. Right? So for the first person, it's going to be a beta. Well, they had 3 in each one, so it's 120, and then this one is 183. Right? 183. Whereas this person over here had a lot more prior information. So we got 120 successes, and they started out thinking that was 30, so it's 150, and this one, they started with 10 and had 180, so it's 190. So I can show you one of those distributions. So let's see. Here's this first one. This is going to make the graph for this person. I don't need limits. Make it blue. So there's the posterior distribution for the person who started out with 3-3. Kind of visually, what is your summary of that person's opinion?
40%.
40%, pretty close to 40%. 40% is pretty close, right? Do you want to just give one number?
Range.
You can give a range, right? You can give the posterior interval, right? So we're going to find these couple of points here. So just eyeballing it, 0.3 to 0.5 maybe, you could, if I do it that way, there's a little bit of leeway. But you kind of want to get somewhere in the middle. You don't want to say 0.2 to 0.8 because there's no probability that far. You want to kind of get it somewhat close to that, right? Use the computer to do it. This 95% interval, I've kind of run out of space. I can get this one. I'll just put the interval here, fit it in.
Bless you.
Bless you. Ends up being 0.348 right up to 0.457. Right? And this interval, if you do the same thing, the interval that they would report based on this distribution is shifted up a little bit, 0.389, 0.494. Why is this interval shifted up a little bit higher than the previous one?
They initially thought it was higher.
Right, so the Bayes combines the prior with the data. If the prior is on one side, it kind of pulls it there. It's kind of a compromise between those two, right? So this prior started at 0.5. This one started at 0.75. Right? It's a little bit. Want to see the picture of that thing? So that's this 150. I think. So the points. We'll make that 1. Orange. All right, so that one shifted a little bit, right? You could tell me the means, right? Because it's the alpha over alpha plus beta, using the new numbers, right? So for instance, the average over here, right? 123 over 306. That average ends up being 0.402. Right? This one, you have 150. You add those together, it's 40. With 300 observations, and then 40 was the sum of the numbers before. That's 0.441. Right? Our maximum likelihood estimate, 120 over 300 was 0.4. Why is that one, and this interval, why is that closer to the maximum likelihood estimate? Or the confidence interval we had before? Why is this one further away?
You started with more certainty that it was higher, so it affected our data more, so the first one was more.
Yep. So if the bigger the numbers are in here, the less variance it has here. So the prior is more specific. It takes more data to move away from that. Right? Whereas 3.3 is pretty small. Right? And so the contribution of the data through the x and the minus x is a lot bigger. So the procedures will agree more with smaller prior, but once you have stronger priors, it pulls it a little bit, right, in there. Right, so that would be a contrast for doing that, right? But any questions about? So if you have the formulas to do that, calculate means, variances, right? That's pretty good. So let's say that you have data from 2 airlines, Pan Am and Braniff. There's another airline that's gone extinct. This one had 300 people. Let's say 290 answered here, and they either answered yes or no. Okay. So there's 120, 180, and 130, 160. Okay. And now we want to test. Are the proportions saying yes, I was more stressed than I expected to be, the same in the 2 airlines? So kind of a null hypothesis could be same proportion, the P for yes among the Pan Am. Let's get back to that. The Pan Am is the same for the proportion for the Braniff. Right, this is the proportion yes. Right. The alternative, right, could be that they're different. Right. So if they are the same proportion, how many do we expect in each of these response categories? remember how to calculate the expected numbers? Right there.
You
Observed minus expected squared over expected.
Yeah, well, the statistic we're going to get is going to be the sum over all those 4 cells, observed minus expected squared over
Oh, yeah.
expected. That's going to be our statistic.
It's like the row, it's
Yeah.
the row,
Sum.
the row that the value is in, or like the total of like the row.
Yep. So like
times
if-
the total of the column
Uh-huh.
divided by the total.
Total, yes. Yeah, so
If
there's
that
590 total. Maybe there's some missing data, maybe 10 people there, even just were so frustrated they threw out the survey or something. So, who knows? And then there's 250 here and 340. So if things are equal, you'd expect these 250 to be divided over here according to these proportions. You'd expect the 340 to be divided over here according to these proportions, or you could look at it the other way. Right. So, for instance, one of the expected values, if you took the 300 times the 250 over 590, that'll give this one here. So that expected value is 127.1. This one ends up being 172.9. Right, it's more because you have 340 here instead of 250. 122.9 here, 167.1. They add up to the same margins and the same overall total, which is 250 and 340. So you can, when it's 2 by 2, just compute one of them and then do subtraction and so on to get the others. And then if you do this statistic, right, so you'd have 120 minus 127.1 squared. So 7.1 squared is about, 49, about 50, right? And then divide by 127. So 50 divided by 127 is about 1/2, right? Maybe it's a little bit less than that. So it ends up being 1.4, right, as a total. So as long as these are reasonably high expected values, at least greater than 5 or 10, then our chi-squared distribution is going to work fine. Right? So under the null hypothesis, assuming the null hypothesis is true, this x squared is distributed as a chi-square distribution with 1 degree of freedom, and the chi-square 1 cutoff value is 3.84. Right? That is, so what in the world does this mean? How do you put into words what that is? What I mean, under the null hypothesis, it has this distribution, and this is a certain percentile value. Right?
if the data truly has, if there's no relation between the two variables,
Mhm.
then as long as your data isn't, your chi-squared value isn't more extreme than 3.84, you accept it.
Yep. So, all that all is part of the story. So if we have these data, and you're going to randomly put it in there, right? And it's not associated in any particular way. It's not more likely to get yes or no for one airline versus the other, right? Then you're going to get a x squared or value, right? And that x squared value, if you randomly made many different tables, you get a distribution. That distribution is going to roughly look like a chi-square 1 distribution, probability distribution. And the farther the observed are from the expected makes this thing bigger. So if we're greater than 3.84, it looks like we've got something that is hard to simulate just by chance. It's unusual. So less than the 5%. So if the x squared is greater than 3.84, we were to reject the null hypothesis and conclude there is an association between the airline association. Right? In this case, we don't reject. Here, don't reject. Just the executives for Pan Am, right, get to, still kind of say, hey, but we were lower than you. But it's not statistically significant. Right? So there's a permutation test, right? So if there were smaller sample sizes, right, you might not want to use this chi-square 1 distribution. You might just want to take the 250, right, and randomly assign them according to these rates. So just kind of scramble the data. You can do that by having 300 and then 290 listed in a big vector, right? And then take 250 yeses and 340 no's and just throw them on there, right, in some random order. And some of them will land in the 300 row, and some of them will land in the 290 row. And it's randomly permuting it. And then you can calculate this x squared for the new data and not rely on that chi-square approximation. Right? That's permutation testing. The p-value in this case, using the chi-square 1 distribution, is the probability that a chi-square 1 is greater than our 1.4. What's the chance we're at our point or greater? That ends up being about 0.237. If we do the permutation test, do the equivalent to that Fisher's exact test, but we can describe it a little more simply. The p-value that I get from simulating 10,000 or so is 2.44. Right? Larger p-values, you don't reject the null hypothesis. It's not unusual. The picture, right, the chi-square 1 kind of looks like this, right? And we're here back over at 1.4. That's a big chunk of the area, about they both round to 0.24 under there. So it's right in the middle. It's not unusual. Don't reject the null hypothesis. You could generate these data by simulation. Right? Why are these two kind of similar p-values? Didn't seem to make much difference in this case, but so is there a reason it didn't make a difference? When did the chi-square approximation work well? It's related to normalities, related to larger expected values. P-hat's not too extreme. Right? So the fact that all of these expected values are pretty big, it's kind of related to n times p-hat, n times 1 minus p-hat. They're not really small. If everybody had said yes and only 4 people said no, then these expected values would be quite small, and this approximation wouldn't work so well. But in this case, it's fine. We didn't do it, but there's Bayesian versions of doing this too. You put prior distributions on P1 and P2. Under the null hypothesis that they're the same, you give them the same prior, right, same means, and then you go through a bigger calculation. Another way to do this, and a reason, is you can do things for 2 proportions, right? So you could do a confidence interval for the Pan Am minus the proportion for Branoff, right? That's why we're doing this one. It corresponds to the chi-square. Same data works for both. Right? So if you do a confidence interval for this, say 95% confidence interval, the estimates, I would replace these things with 1 and 2. It's just because it's a little faster to write. The first estimate was 0.4 for Pan Am. It's 45% for Braniff. And so, P1, 1 minus P1 over N1, and then P2, 1 minus P2 over N2 becomes that confidence interval. So 1.96, 0.4 times 0.6 over 300 plus 0.45 times 0.55 over 290. Right. And so calculating that, we get negative 0.128 up to 0.031 as an interval. So what does this interval mean? There's a little bit of rounding that's going on. So this one's rounded off a little bit, so it's not exactly, I don't know. It's just something I noticed. But in any case, what would this interval, how would you describe this interval? Or how would you write a statement saying what it is?
95% confidence that the difference in proportions of yes answers to no answers between the two airlines lies in entropy.
Right. So you can start out with 95% confidence at something, right? And the problem is focusing on the difference in proportions. We're 95% the true difference in proportions, if you had seen everybody in both airlines, you'd get an answer that's most likely in that range. Braniff had a higher rate, so it's negative, so it leans on the negative side. Is it consistent with the hypothesis, the chi-square test?
Includes 0.
Yeah, zeros in here, so maybe they're the same. It is leaning towards one side, but it's not distinctly different. Right? So kind of the same data, but you get two things, right? So I made up one more. So Pan Am, Braniff. Another layer line that's no longer with us is called Kiwi. Flew from New Jersey to Australia, I think. New Zealand, yeah. And so let's say I had 300 people here, 290 answered here, and only 280 answered there. That's 870 in all. So let's say 120 yes, 180 no, 130 yes, 160 no, 140. So Kiwi is doing a little worse. It's a little lower response rate and a little more negative experience. Sometimes those things go together. Actually, that's a very hard problem to deal with in statistics when the response is related to, non-response is related to the response that you might have seen. That's called non-ignorable non-response, and that's one of the trickiest things to deal with. Right? So in this case, we could ask, are the proportions the same for all three airlines? Right? So what would we expect? If I give bigger tables, I often ask you, what's show me how to calculate one of the expected values. Right? So for instance, this first one up here should be not necessarily exactly the same as before. Right? 134.5, 165.5, those things add up to 300. Where did this thing come from? I expected.
Product of the column divided by total.
Right, so you're in this row and this column. So 300 times 390 over 870 gets this. This is a little higher than it was before, right? We've added in another airline that's a little worse, right? So it makes the rate overall a little higher if you combine all these three. It's just a consequence of having the three airlines together. If they're all supposed to be the same, that this third one makes this a little bit higher. If you do the same thing for the others, it actually splits as 130 and 160, so it actually matches that one. 125.5. I probably put a 0 here to emphasize that it's a 0. And 154.5. Right? Here, these add up to the same thing. 280, so on, 390, 480. The chi-square statistic for this one ends up being 5.86. Right? We compare this thing to a chi-square distribution with 2 degrees of freedom. Right? So 3 airlines minus 1, 2 responses minus 1 gets us the 2. Right? Slightly larger tables, so we have to use a bigger chi-square. The 95% cutoff for this one, for 2, the 95% cutoff for this one is actually 5.99. Our p-value is not quite 0.5, 0.0535. So we don't quite reject at the 5% significance. We'd have to say it's not significant. We don't have statistically significant evidence that there's a different rate, but you might suspect that there is. What?
So this is a different rate. This is all of them don't have the same rate.
The alternative, the null hypothesis would be that they all have the same rate. The alternative is there's at least one difference.
Yeah, that's right.
It could be that 2 are the same and 1's different, or all 3 are all different. Not quite. So it's kind of looking like there's a different rate. What would limit our ability to detect that? Well, if things were changed, what type of table or what type of thing would give us a